Hi everyone. In this video we are going to cover section 5.3 titled The Fundamental Theorem of Calculus. And in this section it sounds big, right? Fundamental theorem. This really is a important topic in this, or an important section in this course, because it establishes the connection between derivatives and areas. Those are the two things that we talk about in Calc 1. Derivatives of functions and what they mean, and areas under curves. And that's what we're just getting into now. But this section establishes that connection. All right, and I am going to go through a couple of things that, without a huge explanation of how they are built. Like this first, the fundamental theorem of calculus. It's talked about in two parts. This is part one. I will have a video that I didn't create, but I think it will establish the relationships better. It will better illustrate what is being what we see in the fundamental theorem of calculus. Okay, so this video will be to introduce you to what the theorem is, and then some applications of the theorem. All right, and so here it is, fundamental theorem of calculus. If you didn't pause and read it already. If f of x is continuous over an interval from a to b, then the function capital F, remember that's the antiderivative that we talked about previously, is defined by capital F of x is the integral from a to x of f of t dt. All right, that's how we define capital F. And then f prime, capital F prime, the derivative of the capital function, is my little f function over that interval. Okay, so that's maybe a little bit abstract. But even despite the abstractness, what it essentially does is to establish the relationship between differentiation, taken derivatives, and integration, evaluating integrals, which is what the whole rest of the course is going to involve. And one other important thing to note, in the previous section when we were talking about Riemann sums, right, the result was always an area under the curve. Here it looks like we're kind of establishing a function because we have this x up here as one of the bounds, but really in practical examples, that x will always be a number. It'll be some number from a to b, right? And then that will be an area under a curve. All right, so that's just one key thing that we'll get into. We're just introducing it now. So let's scroll down here and look at our first example. Let me move that one a little bit lower. All right, so we're going to use the fundamental theorem of calculus in this example, use it to find a derivative of a function. If you notice, I just added on something. It probably just magically appeared. There was something missing when I took a screenshot of the notes to include here, the integral sign and then the 1 and the x. So my function is g of x is equal to the integral from 1 to x of 1 over t cubed plus 1 dt. Now, rewriting my fundamental theorem from up above, it looked like this. Capital F of x is the integral from a to x of f of t dt. Okay, so this looks really similar to the notation in the fundamental theorem of calculus. So using that theorem, it said that capital F prime is little f. So in this problem, we want g prime. G prime of x is just what is inside of that integral, 1 over x cubed plus 1. And like that's it. Okay, the problem was set up exactly like the theorem, but it's establishing the relationship between derivatives and integrals. All right, the derivative of an integral is the function itself. The derivative of an integral is the function itself. All right, they, in a sense, cancel each other out. They are opposites of each other. All right, but that one didn't have too much work. Let's see about this next problem. Okay, in the next one, use the fundamental theorem and the chain rule to calculate derivatives. So my capital F function is now the integral from 1 to square root x of sine t dt, and we want to find capital F prime. What makes this one a little bit different, a little bit more involved, is that up here, the top bound is not just an x, it is a square root x. So the way that we deal with that is we're going to say let u, my top bound, equal the square root of x. All right, so for our f, let me rewrite that now. So substituting that in, our f of x function is the integral from 1 to u, and then sine t dt. And when we take our derivative using the fundamental theorem of calculus, this becomes f prime is equal to the sine, instead of t, right? That's what is inside at first. So we're substituting now in our that top bound the sine of u, but times du over dx. That's that chain rule coming in that should kind of look familiar. Actually, if I scroll back up to the previous problem, I'll come back to that, don't worry. If I scroll back up to the previous problem, we had this x here, right? Or actually this x here, I'll circle that one. That replaced the t in the function 1 over t cubed plus 1. And then if I had, times dx over dx, dx over dx, that is just equal to 1. So there is a inherent chain rule there that we don't write down because the top bound is just x. But when the top bound is more than just x, we do have to account for that chain rule. All right, so finishing this problem out, our last step here is to rewrite my f prime of x in terms of the sine of not u, but u is equal to the square root of x times now du over dx. The derivative of radical x, or x to the 1/2, is 1 over 2 radical x. Right, so we've done that one a few times now, so I'm just going to jump right to that result. 1 over 2 radical x. It's a good one to just have locked into your brain somewhere to know that derivative without having to write x to the 1/2 power and then using the power rule. Okay, so that is our answer to this second example. A little bit more involved than the first one. Now we come to the second part of the fundamental theorem of calculus. The first one, a little bit more abstract, a little bit more complicated, but it establishes a really important relationship. Part 2 is how we evaluate definite integrals efficiently. We saw it in the last section, that one example I did. Took a while. It was clunky and lots of algebra. This is the standard way to do antiderivative, to evaluate definite integrals. Okay, so what it says is the fundamental theorem of calculus, part 2, if our function is continuous over some interval, capital F is the antiderivative of little f, then this definite integral amounts to the antiderivative evaluated at b minus the antiderivative evaluated at a. This is how we do definite integrals. We take the antiderivative and substitute the endpoints. It's such a much more efficient process than Riemann sums, but it is equivalent to doing Riemann sums. It gives you the exact area under a region. Okay, and I will have another video that it's optional, the 2 videos that I'll post that will visually establish this connection better than I can do in this medium. So let's scroll down and find our first example. So we're going to use the fundamental theorem of calculus to evaluate this integral that is written out in terms of t's instead of x's. So we have the integral from -2 to +2 of t squared minus 4 dt. All right, and the way that we do this, and I'm going to write a little bit off to the side here to start, I'm going to write that my little f function is equal to t squared minus 4. All right, well, the capital F function, the antiderivative, right? So remember back in 4.10 we did all those antiderivatives. The power rule says that I add 1 to the exponent, the new power rule for integrals, divide by the new exponent, so t cubed over 3, and then minus the antiderivative of 4 is 4 times t. The derivative of 4x is 4. The antiderivative of 4 is 4x. But in this case, our variable is t. All right, so there's our antiderivative. And I'll make a note here. Normally, we would write a plus c when we're doing indefinite integrals, when there's no bounds on the integral. But in this case, we have definite integrals. The answer is an area, so we leave the c off. Okay. Technically, I could write a plus c, but it would ultimately subtract out later. So with definite integrals, we do not write the plus c. So that's just something, hopefully, that we can, with a few examples, with practice, remember when to write it and when not to write it. All right. So the way that the next step, is to evaluate f at one endpoint, 2, and then subtract out f at the other endpoint at -2. Okay, f of b minus f of a with the capital F, the antiderivative function. The way that we'll write this normally, okay, in practice, in examples, is I'm going to say that integral is equal to what was it? T cubed over 3 minus 4t in parentheses, and then I'm going to write a vertical line, a -2 at the bottom, and a +2 at the top. And that's a straight vertical line, not a curvy one. And what that means is this is my antiderivative evaluated from -2 up to +2. And we always substitute in top minus bottom. So this is like what's going on, what we're doing, and on the left is just kind of how we write it in practice. So substituting in my top bound, 2 cubed over 3 minus 4 times 2, there's the top bound, minus the bottom bound, -2 in parentheses cubed over 3 minus 4 times -2. Scroll up a bit, and then simplifying, let's see what we get. Let's go with green. 8/3 minus 8. That the -2 cubed stays negative, so it becomes plus 8/3. And then minus, minus, and minus is a -8. So 16/3 minus 16, right? This gives me 16/3 minus 16 is equal to -32/3. So that integral evaluates to -32/3. And let me move over to the right here. If we look at a graph of this, I'll just sketch a real quick graph. Here is at -4, and the x-intercepts are at 2 and -2. It's a parabola shifted down 4 units, poorly drawn one. We've got this area. So our result is negative because all of that area lies below the t-axis. Okay, that's why we get a negative for the area. All right, there we go. So that's what we find, and this is how we're going to do it from here on out, how we're going to evaluate integrals. Let's do another example. Evaluate the following integral using the FTOC part 2. And this is another one where I have to add on what the integral is, just something with the screenshot didn't work out nicely. This is the integral from 1 to 9 of x minus 1 over radical x dx. And if we're doing this one, let me write it out first. 1 to 9, x minus 1 over the square root of x dx. Notice this one's a fraction, right? We don't have a quotient rule or a product rule for integrals. So you have to do out the product or the quotient in order to move on, or in a later section we'll learn something called U substitution. We're not just going to look at each of these 3 terms individually because they're not 3 separate terms. They're connected as one fraction. All right. What we do is we're going to split this up into 2 separate fractions, x divided by radical x and minus 1 divided by radical x dx. If you simplify that, the first one gives me x to the 1/2 power because that's 1 minus 1/2. And then here, this is x to the negative 1/2 power. Still writing the dx because I didn't take the antiderivative yet, but now I can. I've got x raised to an exponent. Okay, so the power rule for antiderivatives. We add 1 to the exponent, divide by the new exponent. So this first term becomes x to the 3/2 over 3/2 minus x to the negative 1/2 plus 1 is positive 1/2 over 1/2. That goes in parentheses, vertical line 1 to 9. So that function evaluated from 1 to 9. Before I substitute in, I want to simplify because I have complex fractions, superfractions. The denominators flip up, 2/3 x to the 3/2 minus 2x to the 1/2. And now we are good to go with plugging in our bounds. All right, always, 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 top bound minus bottom bound. 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2. That's my top bound. Minus the bottom bound, 2/3 1 to the 3/2 minus 2 times 1 to the 1/2. Working in the 1 parentheses, I think, is a little bit easier because it's just 1 raised to a couple exponents. Ooh, that's a bad bracket. Let me fix that. So this is just 2/3 minus 2. Because 2/3 times 1, 2 times 1. And then in the first bracket, what do we get here? This is the root. So the square root of 9 is 3 cubed is 27. So 2/3 times 27. This is just the square root of 9, which is 3. Minus, so it becomes 2 minus 2 times 3 is 6. Okay, so I've done out some of the arithmetic there. Now I'm just going to say, poof, I typed it all into my calculator, and the answer is 40 over 3. And you can absolutely use your calculator to help when evaluating these. And then just finally, to connect it to the visual, if you pull up a graph of this function, it looks like this. And we're going from 1 to 9. And here is my f of x, x minus 1 over the square root of x. And we've got that this area is equal to, what's 40 divided by 3? 10, 13, I think 13 1/3 approximately. So the area of this region is about 13 1/3 if I did my mental math there correctly. Okay, so that's what we've found by evaluating this integral. And again, moving forward, this is the process for how we evaluate definite integrals. We take the antiderivative, substitute in top endpoint minus bottom endpoint, and then that gives you the area. And so those 4 examples, that kind of closes it out. We got 2 for part 1 of the fundamental theorem of calculus, 2 examples of part 2. In terms of, like, if you understood the first part like a little shaky, the second part made more sense, that's okay. The second part is really what you have to key on moving forward. Part 1 establishes the connection. Part 2 is how we do it in practice. All right, that is it for this video. Start working on some homework. Please let me know if you have questions. Thank you very much for watching. Have a wonderful day.